Okay, so let's see, 29 seconds. This is good. So in case you have a coma, start again from here.
So in summary, when you write a Spark program, use the master parameter to specify the number of workers. When you create an RDD, you can specify the number of partitions for that RDD, and Spark will automatically create that RDD spread across the workers. When you perform transformations and actions that use functions, Spark will automatically push a closure containing that function to the workers so that it can run at the workers.
Okay. Okay, so I don't know, how many of you have tried to do the 005 notebook? Good. Okay, good. I'll assume others will, because then we can just do more stuff. Okay, so let's go to 006. That's our main notebook for today. So at this point, everyone should have loaded the State of the Union addresses into their Community Edition BBFS, the Databricks file system, which is a wrapper on many distributed file stores. Okay, and make this a tiny bit smaller. So this originally comes from a particular URL. So we basically went to that URL and grabbed the data and loaded it. So this BNAS paper is quite interesting. It's like a digital humanities thing. So they're looking at lexical shifts and what were interesting concepts through time across various presidential addresses and so on. So I don't know, I guess you can see, so these are periods in the x-axis, period 1 through period 10, sort of broken down the years into chunks. And I guess initially negotiations and parties, minister and treaty. This is like all the Native American treaty negotiations and stuff like this. So these words sort of come up and things are changing, after World War II. So here we go, Navy and coast, Navy and sea, weapons and air, and so on and so forth. Okay, it's an interesting paper. So we are simply going to play with this on a word count level. So let's watch this. So this is about types of data.
So in review, the big picture is we have a data warehouse. And from that data warehouse, we'd like to extract data products, analytics, and business intelligence. We get information into the data warehouse by performing extract, transform, and load operations on application databases, files, and logs. Now, some of the key data management concepts that we want to consider are a data model. This is a collection of concepts for describing data, and a schema, which is a description of a particular collection of data using a given data model. Now, information spans a structure spectrum, ranging from unstructured or schema never data. This is information that has no structure and never will have structure. It includes things like plain text and media. Semi-structured or structure-later data includes things like documents, extensible markup language content, and tagged text or media. The last structure element is structured data, and this is schema-first data. This includes things like relational databases and formatted messages. Today, we will look at semi-structured data or schema-later data, where we apply a schema after we create that data.
Okay, so can you guess what data set the State of the Union addresses are that we loaded? Yeah, it's unstructured, right? It's plain text. What about Twitter? What do you think Twitter's? Where in the structure spectrum will Twitter?
Semi-structure, if you use that.
Yeah, so it's kind of semi-structured, but it's even more weird because I guess since the European Union made the IT companies last March to abide by some regulations to fight fake news and and then forget me, right to be forgotten rules and things like this for European citizens. Twitter, I started noting this. So it has new fields, right? New keys that will say like this, whatever should be removed, this user or whatever should be removed from this point onwards or something like this. So this means, of course, Twitter can do this because, they have some, I only see Twitter feeds via JSON or JavaScript object notation converted thingies and string. And you can see that they introduce new fields. So that means if you're collecting Twitter data and new fields come about, then the schema itself evolves, right? It's sort of semi-structured to structured spectrum, but the schema itself evolves, which means, I don't know what database guys actually do, but so the way we kind of dealt with it is very naive. We basically put all the JSON string in one column as a string, the whole JSON object as a string in one column. You will see later what I mean by columns in this sort of Google Parquet files, and then maybe the user ID or something in the first column. So then what we do is we just dump everything into this distributed file store, basically Parquet, and then later on when we read all of that directly using methods you'll see later in this class, then this data frame API in Spark will automatically infer the schema for you. So as long as you specify, a certain range of files to read, it will actually infer the schema by essentially hitting at random enough files to make sure that there's a schema constructed on the fly, and then it will sort of load it for you, which is sort of future-proof, because if there are new fields introduced in the future, then as long as my window of time that I'm looking at the tweets is whatever it is, it will definitely create the the schema for you on the fly as well. But anyway, so these ideas you learn in a database course, right? So most of you here probably have taken database courses. So this is mostly for the math students, like just enough about some swear words, right? So okay. So you don't need to watch this, but we just have to be slightly aware of the file systems and the hierarchies and so on in your local file systems and so on. But because we're doing it in Databricks, it's all abstracted away, and later on, even if we dive into a Docker container with the whole of Spark pulled in for you with Hadoop all in there for a 6 gig Docker container, it's abstracted away, so we can still work on the same Unix file system, even if you're working in Windows. So it's not okay. So here we have the Databricks file system DB utils, and we've already played with this. So let's just make sure that this file exists. I'm going to attach and run to my. So yep. I have all my files, and I can just scroll down and see that up to 2017 thing is there. Okay. So did anyone go to the original website itself where I pulled this stuff from? Okay, good. All right. Okay, so let us display the head or the first few lines of this. So this is basically the command you would do. So dbutils.fs.head, and then I'm simply asking it to return the first 673 bytes of this file, right? So, you can change this to some other number if you like. So that's just the first 673 bytes. So it's always good to see what's in the head of your file. So here you can just play around, maybe try 1,000 bytes. Okay, so just to get more if you want. So here is the text file method. So this I should be able to control enter or evaluate it. Now I have RDD of strings because the text file method just basically breaks down your file by the end of line character by default. You can also specify to break by something else by default if you want. Okay, so now I'm going to perform some actions on this RDD. And the first thing I would do is simply count. So I have 23 rows here. And if I take the 5, I basically have the first 5 lines. Okay, and I can then just do for each println, which is helpful, just printing it line by line. And I can, because this is not too big, I can do the collect action, so everything comes at me back as an array of strings, right? Where each element of this array of strings is just line by line. And then cache the RDD in distributed memory, because this is a very powerful feature of Spark. So if you're going to reuse something, then you can cache it, provided it can hold this object in your distributed memory, which means the RAM allotted to each of your nodes. This is often the case for lots of problems. So that's what we're doing here. So I'm just reading the text file again and then doing .cache here. Right. So this will, by default, put it in memory. And then if you have lots of RDDs that you're doing .caches on, I think it just does some kind of a round robin thing, like, you know, it sort of pushes things out, pulls things out. But I generally try to unpersist. So the command unpersist, you know, will unpersist it from memory. So it's good to keep an idea of what's there. You can also go to the Spark UI and see memory if you like. So you should try that. We'll come back to that, right? So the Spark UI has a particular location for memory, and then you can see the objects that are in memory. Okay, so once again, just counting. And the point here is when you cached it, it's lazy, so it just knows it should be cached. So if I count it, the first time there is an action on this RDD, then it'll actually cache. So the next time we do it, it won't take 0.93 seconds. It'll be much faster, so 0.14 seconds, right? But the difference is huge when the RDD is really big. So now it's really cached. So now I'm going to just perform other things like take 5 again, and it's a lot faster because it's just coming from random access memory. So let's watch this.
The lifecycle of a Spark program is that you first create RDDs from some external data source or parallelize a collection in your driver program. You then lazily transform these RDDs into new RDDs. You cache some of those RDDs for future reuse, and you perform actions to execute parallel computation and to produce results.
Okay, so and I think I already pointed out that in machine learning, you're just doing some iterative computations. So often you will cache these objects that are necessary for your stochastic gradient descent or whatever fixed point iterations you're doing. So that's very powerful. Okay, so now let's do a flat map. So we take the line and split the line by white space. And then so when we take a line and split it by white space, lots of words will pop out. So that's a one-to-many mapping. For that, you use a flat map. So I'm flat mapping and taking the 100. Okay. So now I have an array of words, right? Or array of white space, single white space split elements of a sentence, which was defined by broken end-of-line characters. Okay, so let's do a naive word count here. So what I'm going to do is take each word and then first map it to word comma 1, right, for the count. And then I'm going to simply use reduce by key, underscore plus underscore, for example, which is my which is the operation I'm asking to be done on the values corresponding to the same key, right? So we saw this before with simple examples in Scala. So I flat map, I get that, you already know what it is. Now I take it, each word, and I map it to word comma 1. So this will be inferred as an integer automatically, 1. Then I'm reducing by key with this underscore plus underscore, which is equivalent to, oops, maybe we should do the less sophisticated word count first. Yeah, so that's it. And then I collect. So now everything comes back to me as an array of key value pairs, where the key is the word and the value is the count, right? So this is, the only difference is now we're doing it in a parallel collection. It's something a little more interesting than just integers we made up earlier. Okay. So when we look at this, we have punctuations and things like this. So we want to remove it. Maybe we only want English words. So to do that, we can use regular expressions or regexes. And so there's a lot of regex magic that's there. We will just use some stuff. So here's an example. So I have a string. That's something that Smeagol says, master, master, it's me, Smeagol. But they took away our precious, they wronged us. Gollum will protect us. And okay, so this is Smeagol having like a crisis and talking to himself. So everyone knows Smeagol, right? So example, replace all. So now I'm basically saying replace all, every occurrence, replace all multiple white space character occurrences with a single white space. That's what this is. //s+ is essentially a regular expression for multiple white space characters. Okay, and then this thing here is kind of the Scala triple quotes, sort of is a string literal. So you can put like single quotes inside there if you like. So what I'm saying here is replace the following punctuations: comma, question mark, period, exclamation, colon, semicolon, and full stop. Yeah, no, that's it. And replace all of them by the empty string. That's what's here. Okay. So and then convert everything to lowercase. So that's at least multiple white spaces are gone and punctuations are gone and everything is in lowercase. So now you can see how this string is looking like. So if you want to do a more sophisticated word count, we just take that stuff, stick it in there. We can do it in Clojure. It's not the most efficient, but it's good enough. It's small data. So I'm flat mapping the line, and you see I'm just using this notation. So this maps to, so I take the line and I do this replace all. So and this stuff, getting rid of the punctuations, making everything lowercase, single white space. And then finally, because I know everything is single white space in the line, I can split by that single white space. So now I should just get words without punctuations in lowercase. And now I do map of x to x plus 1. So each word is now going to be counted by reduced by key, right? So is that clear to everyone? Okay, so this is basically hello world of distributed computing. So now I have, I'm interested in, say, the top 10 words by the frequency. So what was the most frequent word? So here I'm using a sort by method for this RED, and by doing _._2, I'm asking for the second element of every element in my RDD, which is the count, right? And then this false, I think, does it in descending order, because the default sort is ascending order from small numbers to large numbers. So this should make it. And then I collect. So I get an array back of the, I'm getting, all of them, not just the top 10 here. So I think if I remove this, Control X. So the is the most frequent word, and followed by off and so on in George Washington's first State of the Union address. So now I'm doing it in ascending order, but then I don't specify how the keys should be ordered within the ones. So I have all this. So if you really want, you can also do a lexicographic ordering of the keys with the same value and things like this. Okay. So let me just undo this. So we can just basically do all of this together for both George Washington and Barack Obama. So this is basically for Barack Obama of 2016 address. Okay. So yeah, Barack Obama also said the 264 times, a lot more, but I don't know what is the total number of words in the speech, so we don't want to get too excited about raw counts, right? Okay, so now reading all the State of the Union addresses at once using the whole text file method. Yeah, there are these challenge problems in the assignment. Don't do it unless you kind of are bored or want to really get into it, okay? Because they're usually set by me if I'm super bored one day. And, sometimes you feel like you can learn a lot and do a lot. You have all this energy. So, you're not expected to, you're not graded on it. Or TILO. TILO can just make it very interesting very quickly. So if it says optional, then just do the main part if you don't have time. And it's more important to submit relatively on time than to. Okay, so this is very powerful, the sc.whole-text-files method. So I put the star operator, so it says anything that ends with .txt in that directory, right? So this thing should now take all my files. I've also cached this. So, and remember this RDD gives you a tuple, a two-tuple. So the first element is string, which is the name of the file. And the second element is actually the content of the file. Right? So that's what I've done in SOU all, and I've cached it. But of course, it's lazily done with the cache, so I have to count. And actually, this count is the first time it's going to read all of it. And, it might take a while, actually, because, yeah. So there's 231 of them. And then now if I count, this time it's super fast because it's actually cached after the first action. Okay, so now I'm simply taking 2 of these. So now 2 of these are actually the first file, its content, the second file name, and its content, right? So that's what this should be if you dig in. So this is an array, this is the path to the file, and then this is the contents of the file starting here, right? So then if you go down, there should be a point where the second speech starts. Okay, so this is the beginning of the second tuple, two-tuple. So that's the first element of the tuple, and here is the content. Oh, sorry, here's the content. Okay. Okay, so now I'm simply finding the names of the files by saying here's my file contents pair. I'm mapping the SOU all to grab the ._1 is Scala method for getting the first element of a tuple, right? So so this is basically, and I'm collecting it because it's just file names, and so I'm getting an array back with just the paths to all the files. Okay. Okay, so here is let's find the number of words in each of the SOU addresses next, because we can do it. So here is my, I'm going to take my val. So here is here's kind of a little bit of a block. This is now closure. I'm shipping with this map, and I'm taking my file content pair and doing something to it. And what I'm doing is here, right? So well, basically I have one thing, WC, and I'm just returning WC, okay? So what is WC? It's word count. This shouldn't intimidate you now. So I'm taking the contents of the file, contents pair, and I'm playing my game of replacing all, right? The multiple white spaces by single white space, and removing punctuations, turning into lowercase, splitting, right? So now I just have an array, and now I'm going to simply ask the length of the array. So Okay, so let's do WCS. So now this is WCS. So I'm collecting it, and that's the number of words, basically, without punctuations in each file, right? Okay. Yeah, because because you see now my entire file content is a string, so I don't have the end of line delimited extra layer, right? Line by line layer. I don't have that anymore. So I am actually counting the number of words in each State of the Union address. So as you can see, they are getting longer. Trump isn't the longest, actually. Okay. So really, just 5,000 words? Is that right? Am I doing something wrong? Seems right, right? 5,000 words is a lot. Okay. I'm not really trying to look at these notebooks too closely, right? Because some of them are from last year, so I'm kind of just jazzing live here. So because I don't want it to be like too prepared. Okay, so here is some homework. Word count one, sort by, and learning some dbutils .fs file systems. So here's an example. Let's learn a bit more about sort by. So I have my Spiegel's little string example. So once again, I'm doing exactly the same thing, and I split by words. So now an array of words, lowercase. And so what I'm doing is taking this array of words and turning that into an RDD, a distributed resilient distributed data set, an RDD of strings. So now this object is actually distributed. So for example, if you want, you should be able to do RDD. Do you guys remember the command that tells you the number of partitions? Is it get partitions? Something like this. Is it get partitions or? Yeah, okay, get num partitions. So I just tab completed. This should be 8 by default in the community edition. Some optimization they've done. Okay, so we can do a lot more, right? We can do glom and things like this and see which words are in which of the 8 partitions and things like this from first week. Okay, so here is take 10. So I'm just taking top 10. And then now I'm simply playing this reduce by key. It's just the same thing. But if you notice, you see every time I do these operations, my RDDs, because I can only transform, right? And reduce by and take actions. And every time I do these things, I get a different type of RDD, right? Typically. So for example, I started with a RDD of strings here. And then when I'm doing the mapping and the reduce by key, I get an RDD of string and int, right? And it's actually, under the hood, it's really a shuffled RDD and so on. So maybe we'll come back to these things in the second half of the course. Okay, so I'm now doing sort by underscore dot underscore 2 just to understand this thing I told you about ascending order. So you can just see it in a simple example. So it makes sense. Yeah, so I guess we should try to, do things a bit more nicely when you code, so your fellow programmers can understand you. So, so these are, this is slightly a better way of doing this instead of this kind of quick, nice Scala magic. You can write it a bit more cleanly. You can say it's a case of this pair word comma count, and that's getting turned into count, and so on. It's just a lot easier to understand, especially if people are coming from other languages. Okay, so we again just count B23. And I think this should give you enough of a handle to finish the assignment. Some of you already finished it. for a couple of you who finished it and got the solutions, Tilo is working out some strange issues. Apparently, the Databricks, something happens when you attach a DBC notebook to the Uppsala University mail thing. So I don't know. So it does something to the actual file, the attached file. So and Databricks complains. So Tilo is trying to resolve it. So, but several of you submitted got some of the answers wrong. So if you got the first 4 or whatever the main assignments wrong, then I basically send it back to you. You can try any number of times. I mean, I'm manually dragging it into the draft box and hitting reply, so probably don't do it like every 5 minutes or something. And I think Tilo is going to only run the in-house correcting thingamajig maybe 4 times a day or something, so it won't be like instant feedback. But there are tests in place usually, so you can run those tests and make sure those tests pass before you. Yeah, there's no penalty for trying it many times or anything. Okay, so this is essentially how you, I think this is all you need to do the assignments. This week's assignment. Okay, so I think we're having coffee now. Is that right? Yeah. Yeah, so